In this video, we're going to talk about definite integrals and how they're related to area and the fundamental theorems of calculus. Let's remember that in the previous video, we considered this type of problem, which was sort of a new type of problem. We have a function, and we're looking for area underneath that function between two endpoints. And what we found is that one way of doing this is to break this up into rectangles and then find the area of each rectangle, and that gives you an estimate, and then fit in more and more and more rectangles, essentially fit in an infinite number of rectangles, and you are able to find exactly what this area is. I will remind you that, that in the previous video, we found this area to be 64 over 3 using that technique. Now, we're going to start off with a definition here. A definite integral of f of x from x equals a to x equals b is denoted by this elongated s right here. We call this an integral from a to b of f of x dx. So this is just notation. This represents the area under the curve of f of x over the interval from a to b. So if we go back and look at this problem right here that we did, we know that this area that we found actually is represented by the integral from 0 to 4, right, because we go from 0 to 4 here on the x-axis. Our function in this case is x squared. That's the area is underneath this curve of x squared. Dx is just part of the notation. And so this is what we actually found. This is equal to 64 over 3. And at the moment, this is just notation, all right? So we aren't really seeing how to do this yet unless we go back and we do that rectangle thing, which is kind of long and complicated, and that's not the way that we'll really do things. All right, so if we're just talking about in general here, let's just see here. We got some kind of a graph, and the function could look like whatever, some weird looking function here. And this area that's underneath here from a to b is represented by this definite integral. And so what we're going to do is we're going to go on to find out, well, how do we actually find the value of this thing? All right, and I want to start with the first fundamental theorem of calculus. Okay, the first fundamental theorem of calculus here, which states that if we take the derivative of the integral from a to x of some function f of t, now don't let the t bother you here, that's just a dummy variable anyway, it doesn't matter what that variable is, then that is equal to f of x. So let's break this down just a little bit here, okay? Let's just sort of cover up some of these things, all right? F of t is just some function. And if I take the integral going from a to x, so a is just some constant, whatever it is, 0 or whatever number we want that to be, up to some number x, and x up there is just some number as well. So we know that this represents an area. And so if we take the derivative of this, then what we're talking about is the rate at which that area changes. And this theorem is saying that the rate at which that area changes is equal to this function at x. Now, let's go over here to Desmos. And I've kind of programmed this to sort of go in here and just sort of visualize this. Let's say that we got some function here. I don't know what function that is, just f of x. And if we go from 1 to 2 and look at the area underneath this function, over here off to the side, you can see that area is equal to 4.8. But if I take this and if I drag it over, notice how that area changes, right? It changes because the region is larger. And so from 1 to 3, we get an area of 9.6. All right, so the question is, at what rate does it change? Well, going from 1 to 2, we can see that it went up, a bit. Going from 3 to 4, 9.6, the area changes up to, what it looks like it goes up to 11.8. I want you to pay attention, if I go from 4 to 5, pay attention to how much this changes. You're going to see it's not going to change by very much, right? From 3 to 4, we went from 9.6 up to 11.8, so, a little bit more than 2. From 4 to 5, it only goes up to, let's see, what is that? From 4 to 5 only goes up to 12.4. It didn't change by very much. Now the question is, why didn't it change very much? The reason is we don't have a lot of area here, right? This region right here doesn't contribute much to the area of the overall region. And so, why don't we get a lot of area? The reason is because the function is not very high there. Your y value is really pretty close down here. You're not getting a lot of area. Whereas if I go from 5 to 6, I'm going to get a lot more. And the reason is that the function is higher up there. So what we're seeing is that the rate at which this area changes with respect to the whole region, the rate at which it changes depends on how high the function is. In other words, it depends on the function value at that value of x. And that's really what the fundamental theorem of calculus is saying. It's saying that the rate at which this area changes with respect to that x value is equal to the height of that function at that x value. Okay, so we got the first fundamental theorem of calculus. And yeah, it's an important thing, but really where this comes into play is in its implications. And so we're going to consider the implications of this. All right, so if we accept this to be a fact, if we say, all right, yep, when we take the derivative with respect to x of this thing right here, this quantity, and if that is equal to little f of x, then what that means is that this integral, this definite integral from a to x, this is an antiderivative of f of x. Okay? What we're saying is that if this is true, if the first fundamental theorem of calculus is true, remember, if you have a function and you take the derivative of that function to get another one, that original function, that's the antiderivative of it. And so we've just found an antiderivative here. Okay. So if that's an antiderivative, I'm going to call it something else. I'm going to call it capital F of x. All right, sometimes we use capital F of x as our antiderivative. So capital F of x, that is equal to the integral from a to x of f of t dt. Okay. And it is a function of x. Remember, it is a function of x here. If I go in here and I've got some kind of a function, f of t, that doesn't change. That's just some function. A is just some constant down here. The only thing that's really changing is x. If I pull x off to the right or off to the left, or if I move it anywhere, then this area right here is changing. And so it depends on x. So capital F of x is equal to this integral right here. And so I'm going to write something down here. Now don't worry about where this comes from. I'm just gonna write something down here. I'm going to write down capital F of b minus capital F of a. And I just want to see, well, what does this thing turn out to be? If I define f of x to be this, hey, I'm just going to plug some different things in here and see what it turns out to be. Well, capital F of b would be the integral going from, this constant a to this constant b. All I did was put a b where the x is of this function. Okay? And I'm going to subtract off capital F of a. Well, that would just be putting a where the x is. Okay, so I've just written that down. But now let's think about what this is. This part over here would be the area underneath the curve of f of t between two constants, a and b. Well, what about this one right over here? This would be the area under f of t between constant a and another constant a, and that's the same constant. In other words, if we just kind of think about what this looks like over here, here's f of t. We're going from a to a. Well, there is no area under that. That would just be a very thin, tiny little line. That's just a single point underneath that curve. There is no area associated with that. In other words, this thing right here is 0. And so what we see here is we see that f of b capital F of b minus capital F of a is equal to this definite integral between a and b of f of t. And what is that? Remember what that capital F of x is here? That's an antiderivative of this little f of x. This gives us a way of evaluating these definite integrals. So that's what we call the second fundamental theorem of calculus. All right, what it says is that if I am looking for an area underneath the function between two constants a and b, then, okay, and I'm going to go back to x's here. Remember, that was just a dummy variable, so it doesn't really matter. Okay, if I'm looking for the area under f of x between a and b, then I can find that by doing just a subtraction here of capital F of b minus capital F of a, where capital F of x is an antiderivative of little f of x. Okay, well, that's the second fundamental theorem of calculus. And that one is really important. That one is used all the time. So let's actually go in here and see that at work. Let's see an example of it. I'm going to go back here to our favorite example. And I'll just remind you, hey, how did we do this before? Or remember before when we did this, we broke that thing up into lots of different rectangles. We said there were n of them. We found the width of each rectangle. We found the height of each rectangle. We used the widths and the heights to find an estimate of that area. And so we went in and added up from 1 to n, the width times the height. We did lots of algebra. We got all the way down here and sort of simplified it to here. And then we said, okay, well, let's let n head off towards infinity. And if n heads off towards infinity, then what happens is that we end up with 64 over 3. And that was how we did that before. A lot of calculation, very involved. Let's see if our new technique here is a little bit easier. All right, so remember what our new technique is that we're going to find an antiderivative of little f of x. We're going to plug in the two constants, and we're going to do some subtraction. So, all right, here we go. We know that the area is the definite integral between 0 and 4 of x squared. That's the thing we're trying to find. We know that an antiderivative, because we know how to find antiderivatives, we just add 1 to the exponent and we get the same number downstairs. So an antiderivative would be x cubed over 3. And if I want to write that as a general antiderivative, I'd need to add a plus c to that. And so the area is equal to capital F of 4 minus capital F of 0, which is, let's see, that would be 4 cubed over 3 plus c minus, now I'll stick the 0 in, 0 cubed over 3 plus c. Looks like what I get here is 64 over 3 plus c minus, that's just going to be 0, so that negative applies to that. Looks like we just get 64 over 3. Wow, much easier than doing all the rectangles and everything. And that's how we apply the second fundamental theorem of calculus. Now, I do want to do one thing here. I want to sort of rework this problem. I'm just going to do exactly the same thing here, except for I'm just going to sort of use a little bit different notation. I'll show you the way that we usually denote this stuff. So let's go back to what we were trying to find. We were trying to find the integral from 0 to 4 of x squared. Okay, I'm not going to do anything different other than just kind of write things down a little bit differently here. I know that an antiderivative of that is x cubed over 3. And one thing that you could see by doing this up here was, you know, adding that plus c didn't really do anything because the c's just canceled out anyway. And that will always be the case. If you're doing the general antiderivative here, then the c's are going to cancel out when you go in and subtract these two things. So I'm not even going to worry about the plus c. I'm just writing down the n antiderivative here. Okay? I'm going to put this long line right here with a 4 up on top and a 0 on the bottom. And what that notation means is that whatever is to the left of it, whatever expression is over here, I need to stick in this number, and I need to stick in that number, and I need to do the subtraction between those two quantities. So this represents 4 cubed over 3 minus 0 cubed over 3, which is where we get the 64 over 3. And that's just kind of how you'll see things written when we do these things. Okay, so that's definite integrals for finding areas underneath a curve between two constants. We saw how to write these things down. We saw the first fundamental theorem of calculus, and we saw the second fundamental theorem of calculus. And the second fundamental theorem of calculus in particular is the one that allows us to find these areas in a pretty straightforward and easy way. So I hope that's been helpful. Best of luck to you.